Hello and welcome to section 6 of CSE 373. This section will be all about graphs, so reviewing the graph terminology / fundamentals, and then going over graph traversal in the form of BFS, DFS, and Dijkstra's algorithm. Let's hop into it. For course announcements, the late due date for exercise 4 was May 4th. P3 is due next Wednesday on the 10th, as well as your midterm resubmissions. There won't be any, you won't be able to use any late days for your midterm resubmissions, so please make sure to get those in before it closes Wednesday evening. And then the late due date for P3 is Saturday. Awesome, and exercise 5 is out. Let's hop into some graph intro. So if you were to boil graphs down to its simplest form, a graph is literally just a set of nodes, which are also called vertices, and a set of edges, which connect to nodes or vertices. So each graph has a set of vertices, a set of edges, and then vertices that are connected via an edge are called adjacent vertices. The degree of a vertex is the number of edges that are directly connected to that vertex. So if you're looking at this vertex right here, the degree of this vertex would be 1, 2, 3, because there are 3 edges coming into / out of this vertex. And then a path is a sequence of vertices connected by edges. So a sequence of adjacent vertices. And then a cycle is a path whose first and last vertices are the same. So if we were to look at this graph down here, there would be a 3 cycle between this vertex, and this vertex. 1, 2, 3. Great. And then a graph that contains a cycle is known as a cyclic graph, and a graph without any cycles is an acyclic graph. As well as graphs come in 2 flavors, directed and undirected, where undirected graphs, edges don't have a connection. So there can be at most 1 edge between any pair of vertices. However, for directed graphs, edges will start at a vertex and then end at another vertex, going from one direction to another. So in this case, there's a path from vertex A to vertex B, but there isn't an edge from vertex B to vertex A. And here are the 4 flavors of graphs. Acyclic directed, there's no cycle in this directed graph, right? You can't start at a node, take a sequence of edges, and end back at that node, right? If you were to try that, you would take this edge from A to B, then B to D, and then we'd be stuck at D, since there are no edges coming out of D. For an undirected acyclic graph, it looked like this, because we can't start at a vertex and then take a sequence of distinct edges to end up back at that vertex, right? We can't go from E to B to D back to E because that edge doesn't exist. And if we were to go from E to B to E, that wouldn't be considered a cycle since we reuse this E to B edge. This is a directed cyclic graph because we can follow distinct edges and end up at any vertex. And here's its undirected cousin, where likewise you can follow a series of distinct edges and then end up back at any vertex. And there are so many applications for graphs, such as physical maps, right? Airline maps, traffic. Graphs are also great at showing relationships or dependencies. So like you can imagine that your social media followers and the people who you follow will form a graph, where there's an edge coming out of, let's say, your vertex to somebody you follow. And if they follow you back, there will be an edge going from them back to you. It's really cool. Some related topics are also like web page rankings. If a website is linked by a bunch of other websites, we can represent that via a graph, where each website is its own vertex. And then if one website links to another, we can form an edge from that site to whatever site it links to. And so many more. Super cool. Yeah, so I would pause the video here and give problem 1 a go. All right, I'm going to assume that you at least looked at these problems, and now let's walk through the solutions. So the problem asked us to consider this undirected and unweighted graph below. Well, we can tell this graph is undirected because the edges don't have arrows on them. And we can see that this graph has unweighted edges, which means that there are no weights or numbers associated with each edge. We will work with weighted graphs later on during the Dijkstra section of this section video. Problem 1a asked us to find V, E, the size of V, and the size of E. So the set of edges in this graph, the set of vertices in this graph, and then how many vertices do we have, and how many edges do we have? Well, to find the set of vertices, we just have to look at each vertex in this graph. So it looks like all the vertices in this graph are A, B, C, D, E, F, and G. How many edges do we have? Well, it looks like there's an edge from D to G, E to A to B, B to C, C to F, and F to B. And because this is an undirected graph, we can also flip the order of two vertices in an edge and it won't change anything because there's no difference between an edge coming out of a vertex and an edge going into a vertex since this is an undirected graph. However, with directed graphs, we'd have to make that differentiation. Great. How many vertices do we have? We have 7 vertices. 1, 2, 3, 4, 5, 6, 7. And how many edges do we have? We have 1, 2, 3, 4, 5, 6 edges. And that's how we arrived at this answer. What is the maximum degree of this graph? Well, remember, a degree is just the number of edges coming into or out of a vertex. And in this case, we can see that B is the only vertex that's connected to 3 edges. So the maximum vertex in our graph is 3. Are there any cycles? And if so, where? Well, we don't see any immediate cycles in this left portion of the graph. But right here, we see a 3 cycle, where you can start at any one of these vertices, so B, C, or F, and arrive back at itself by following these 3 edges. So there is a cycle between B, C, and F. What is the maximum length simple path of this graph? Well, we covered what a path is, which is just a sequence of edges, right? But a simple path is a path where we don't repeat vertices. So let's try and find the longest simple path. Well, it looks like there's only the longest path in this connected component of the graph, which is just a portion of the graph where you can get to each vertex, right? So we have 2 connected components in this graph, one between D and G, and one between this other half of the graph. Well, there's only one edge, or the longest path in this connected component is 1, so it's probably not here. How about on this other connected component of the graph? Well, if we're looking at this, it looks like we can create a length 1 path from E to A, and then follow the edges until we end up over here on the right side. So this would be from E to A to B, B to C, and C to F, with a longest length simple path of 4. 1, 2, 3, 4. We couldn't have made this 5 by adding the edge F to B, since we can't repeat vertices in a simple path. So that's our answer. The max length is 4, and there are several simple paths with maximum length. For example, if we went from B to F and F to C instead. What is one edge you can add to the graph that would increase the length of the maximum length simple path of the new graph to 6? Well, looking at this graph, we could definitely increase the longest length simple path by adding an edge from D to E. This would increase the length of the simple path from 4 to 1, 2, 3, 4, 5, 6. And that's our answer, connecting the 2 connected components of our graph. And then what are the connected components of the graph? Well, I gave this away earlier in the video, but the 2 connected components are D and G, and then all the vertices over here, which are E, A, B, C, F. Awesome. Moving on to 1b, it asks us to consider this undirected but weighted graph. So now each edge has a corresponding weight or value. What is the path involving the least number of nodes from E to C? And what is its cost? The path involving the least number of nodes, starting at E, would be from E to A to B, and then B to C. So there would be 4 nodes in total. And what is its cost? Well, that's just adding up the weights of each edge in this path. So that would be 6 plus 7 plus 8, which is 21. what is the minimum cost path from E to C? And then what is its cost? Well, the path we just found is 21. Is there a shorter path from E to C? Well, let's check it out. So we can go from E to A and A to B with a cost of 13. And the only other edge we can take that doesn't lead us to B to C is to F. So let's take that. So we add this cost of 2 to our running total to arrive at a cost of 15 so far. And then we can take this edge from F to C with a final cost of 18. And this is the minimum cost path, which has a cost less than the path with the least number of nodes. And then what is the minimum length path from E to C? And what is its length? And this is different than the number of nodes. It's the least number of edges. So the path with the shortest length would be from E to A to B, and B to C, which is exactly the path with the least number of nodes, least number of nodes. But in this case, we're just wanting to choose the path with the least number of edges, which will more likely than not end up being the same path. But in this case, we count length by the number of edges we took, and we took 3 edges to get from E to C. So this is the shortest length path. All right, let's dive into some depth first search as well as some breadth first search. So this is the pseudocode for a breadth first search, where we're going to explore a graph level by level. We're going to first explore nodes that are really close to our starting vertex, and then slowly branch out from there, exploring nodes that are farther away. So we're going to do this by using a queue that we call queue in our pseudocode, and then we're going to add the start vertex to our queue. And then we're going to mark that start vertex as discovered. So initially, all vertices are undiscovered, and as we slowly discover them, we will mark them as discovered. So that way we don't repeat vertices in our breadth first search. And then we'll eventually explore all vertices that are connected to our start vertex by repeating this while loop until our queue of vertices is empty. So while it's not empty, we're going to remove / explore one vertex from our queue. And then for every edge that's connected from the vertex we just removed, as long as it's not discovered, then we're going to add that vertex to queue and then mark that node as discovered. And we're going to repeat this process until we've discovered all nodes. And since we're using a queue, we're going to explore nodes in the order that we find them. So we'll first explore the start node, and then we'll explore its children, and then we'll explore those nodes' children. And this is how we end up with a breadth first search, where all nodes closest to our start node are explored before nodes that are farther away. And here's the actual code. As long as you understood the pseudocode, then there shouldn't really be any surprises here. It's just basically explicitly written in the actual code where we're creating queue. And then the way we're discovering vertices is by adding it to a set of discovered vertices. And initially, we're adding our start vertex to our queue, and we're marking it as discovered by adding it to our set of discovered vertices. And then the code inside is basically exactly the same as the pseudocode. And then for DFS, literally the only thing that's different is that we're using a stack instead of a queue. This is how we result in a depth first search, where we follow an edge to one vertex and then follow another edge to that one of the children of that vertex, and keep going down and down until we hit like a leaf node in this tree that we form, or a vertex in this graph has no outgoing edges. And then we'll go back up a level and explore all of that node's children. So this is what we refer to as a depth first search, where we follow like a path deep down into the graph and then pop up, like exploring a binary tree instead of exploring level by level in BFS. And the way we accomplish this is by using a stack, right? With BFS, we use the queue. So we would discover a node, add it to our queue, and then we would explore the next node that we discovered. And then we would explore the next node, the node that is next in line to be discovered, or the one that's been that was first into the queue, or next up. However, with the stack, the node that we're going to explore next is going to be the one that we just added to the top of the stack. So we will repeatedly explore the latest node that we added to the stack, as opposed to it being added to the end of the queue. So that's how we end up with this depth first search behavior. Here's the pseudocode for DFS. And notice that it's exactly the same, except for the data structure we use to host nodes that we're going to explore is the stack instead of a queue. And everything else is exactly the same. Great. Pause the video here and see if you can run through BFS in problem 3, and then I'll go over it. Awesome. Let's walk through BFS. So here's the start state of our BFS, where we added our start node S to this queue of vertices we're going to use. And nothing else has happened yet. So we're going to take S out of that queue and mark it as processed or discovered. This is our set of discovered nodes. Now we're going to explore or add each of its children to this queue. So we add Y and T to our queue because those are the nodes S is connected to and are not discovered. Additionally, you'll also see this column called pred or predecessor, which is basically, this is how we're going to form our BFS tree. If you look back at a couple of slides, this tree over here is what's referred to as a BFS or breadth first search tree. And what's really cool about this tree is that it kind of divides nodes into levels. So every node that appears at this first level has a shortest path that is 1 or distance of 1 edge away from the start vertex. And then all the vertices at this next level or third level have a shortest path of 2 edges away from our vertex. So the way we'll generate this tree and also find the shortest path is by keeping track of the node that is its predecessor while performing a breadth first search. So because we added T and Y to our queue, after processing S, we'll store S as T and Y's predecessors in our table. Next, we'll take T out of the front of the queue and explore it. So now we mark T as processed, and since it has edges to Y, Z, and X, we'll add all of these nodes that aren't processed or explored yet, or discovered. So many synonyms. So since we already discovered Y, we will not add it to our queue. However, X and Z we haven't seen yet, so we'll add these to our queue. The next node we're going to process is Y. Oh, and one more thing. Notice how now T is X and Z's predecessor in our BFS table. That's because we added these to our queue when we were processing T. So keep that in mind. Now we'll process S, and S has 2 nodes, or 2 edges, one to Z and one to X. Both of these vertices we've already seen at least once, so we're not going to add Z or X to our queue in order to avoid double processing a node. Next up, we'll process X. X has a single edge to T, however, T has already been discovered and processed, so nothing will happen. Finally, we'll process Z, and likewise, it has a single edge to X, and X has already been processed, so nothing will happen. And then this is the resulting spanning tree, or shortest path tree in this case, that our BFS has generated. And we can observe these edges or find these edges by starting at the vertex and then following its predecessors back to the starting node. So in this case, to find the minimum spanning tree, shortest path tree in the case of BFS, we could, for example, start at X and then follow the chain of predecessors. So there'd be an edge from X to T. We'd hop over to vertex T and find that its predecessor is S. So in this case, we can observe that that edge from X to T and T to S is in our BFS tree. So these 2 edges. And for the other vertices, we can do the same. So there must also be an edge from Z to T And there must also be an edge from Y to S. And these edges will create or result in our shortest path tree that was shown in the BFS slide. And how do we interpret this final table? Well, this is kind of the process that I just walked through. Essentially, we can locate a target vertex and then follow the chain of predecessors to see if there's actually a path between this the starting vertex and the vertex that we're curious about. And then to find the shortest path tree, we do the same process, but for all the vertices, which if we follow the individual paths from every vertex to the starting vertex, then all that set of unique edges will be our shortest path tree. Awesome. Now for 2, the problem just asks that if we traverse this graph using BFS starting at A, what are the 2 possible orderings of the nodes that we could end up with once we run the algorithm? And then the second part of this question asked us the same thing, except for if we use DFS than BFS. So I'm not going to dive into the individual orderings, but the key concept behind this question is understanding how we can end up with different node orderings, right? So in our BFS tree, level by level, the nodes at each level will be the same. However, there could be variance in how we choose the order of nodes that we process that are the same level away from our start node. So for example, the 3 nodes that are 1 edge away from A are C, F, and B. And the order in which we process these is different depending on whether we add F to our queue first or C in our queue first. Because whichever one we add first, we'll end up exploring its children first. And those children will end up in our ordering before the children of the other node. So that's how we can end up with a different ordering of nodes in BFS if we chose F instead of C in this example. And then the second ordering would be the result of choosing C before F to process in BFS. And then it's exactly the same for DFS, where if we chose to explore F first or G first, we would follow this chain of nodes back to A, since there's no edge from G to any unexplored vertices if we were to explore F instead of C. And then if we chose to explore C first, we would explore C and its 2 children before popping up to A and exploring any of the other nodes. So that's how we can end up with a different ordering as well for DFS. Really just boils down to which next node do we arbitrarily choose to process next within the same level. Or in the case of DFS, it's which node do we choose to process that's 1 away from A. Awesome. Let's dive into Dijkstra's. So we just spent quite some time learning about BFS and DFS in depth. BFS is amazing for generating the shortest path tree or finding the shortest path between some start node and another node or any other node in the graph. However, BFS only works if all edges are treated the same and we're working with an unweighted graph. If edges are weighted and different edges have different weights in a weighted graph, then BFS falls apart. It will give us the path with the least number of edges from one vertex to another. However, what if we wanted to find the shortest path in terms of cost from one vertex to another vertex? This is where BFS falls apart. And instead, we'd have to use another algorithm called Dijkstra's algorithm. So this is how we perform path finding on a weighted graph. And the main idea is to find the shortest path or the shortest distance from the start node in our graph to every other node you can get to in that graph. And we can see the resulting minimum cost tree here, which contains the minimum cost path from S to every other vertex in this graph. And if we implemented BFS with a queue and DFS with a stack, Dijkstra's is the algorithm that uses a priority queue. Its structure is very similar to the other graph traversal algorithms, but now the underlying data structure is a priority queue. And inside of our priority queue, the priorities of nodes are their distance from the start of the nodes, where nodes with a shorter or less distance will be prioritized over those nodes that are farther away. And then essentially what this algorithm is pulling the closest node off of our priority queue in each iteration, updating the distances for its adjacent nodes, and then discovering that node by adding it to our set of discovered nodes. We're essentially applying the same rule at every single iteration of our algorithm, which is choose the closest undiscovered vertex, add its edge and that vertex to our set of discovered nodes and our minimum cost tree, update distances and repeat. And we'll repeat this single rule greedily until we've discovered or added every single vertex in our graph to our set of discovered nodes, and until we generate this minimum cost tree. Here's the pseudocode for Dijkstra's. There's one additional component in Dijkstra's than the other graph traversal algorithms, and that's node distances. So we'll initialize all nodes that have a distance of infinity, and over the course of the algorithm, we'll be updating that node's distance as we discover edges to a given node. So we initially initialize all node distances to infinity. And then next, we mark all vertices as unprocessed, just like in BFS and DFS. And we update the distance of the source vertex to 0, since our starting vertex has a distance 0 away from itself. And then while there are unprocessed vertices, we'll pluck the closest unprocessed vertex off of our priority queue. We'll explore all of the edges going out of the closest unprocessed index, and we'll update its distance. So if its current distance, v.dist, is greater than the distance of the current node we're at, plus the weight of the edge from the current node to its neighbor node, then in this case, where this new distance is less than the original distance, we're going to set that original distance to this newly found shorter distance, and then change the predecessor of this node. Since we discovered a shorter path than what the node originally had, its original predecessor will no longer lead to the least cost path in our least cost path tree. So that's why we changed the predecessor here if we ever discover a shorter path. And then finally, we will mark the node that we took off of the priority queue as processed. Cool. I feel like Dijkstra is super complicated the first time you see it, but I feel like walking through Dijkstra and seeing the decision-making process and updates at each step will really help cement this algorithm, if you will. So let's do that. So here's our initial starting graph. We're going to perform Dijkstra's starting at vertex S. So we will process vertex S and then update the distances of any neighbors of S. So in this case, the distance from S to T will be 0. The distance S is away from itself, plus the cost of this edge 6. And notice how we initialized all other vertices to have a starting distance of infinity. Well, 6 is less than infinity, so the distance of T will be updated to 6. And likewise for Y, where the distance of Y will be updated to 7. And since we updated these distances as a result of edge coming out of S to T, we'll set the predecessor of T to be S as well as Y to be S. In order to follow the back pointers back up to S, to 1, find the shortest path from S to these vertices, and then 2, to generate our least cost tree. All right, so now we want to choose the next closest unprocessed vertex, which, as we can see on our distance table, is T. So T will be the node returned from a priority queue, since it has the closest distance of 6. And we will process T next. We see there are 3 edges coming out of T, 1 to Y, 1 to Z, and 1 to X. So the next step will be to update these distances. The distance of Z and X are both still infinity, since their distance has not been updated yet. So now their distances will be updated to the distance of T plus the edge from T to these vertices. So since T has a distance of 6, Z will now have a distance of 6 plus 4, which is 10. And likewise, X will now have a distance of 6 plus 5, or 11. And both of these values are less than infinity, so they will be updated. How about y? Well, y currently has a distance of 7. And the distance of this path from S to T to Y will be the distance T is from S, which is 6, plus this edge, which has a distance of 8. Well, in this case, 14 is not less than 7, so Y's distance will not be updated. But we will update the other vertices, then also marking the predecessors as well. The next closest vertex is Y, since it has a distance of 7 in our table. We will mark Y as processed, and then update distances according to edges coming out of Y. So Y has an edge with cost 9 to Z. Okay, what is the cost of this path from S to Z? Well, this would be 7 plus 9, or 16. Well, Z's current distance is 10, or the distance of the path starting at S going through T and ending at Z is 10, which is less than 16, or the path from S to Y to Z. So Z's distance nor predecessor will be updated. How about this edge from Y to X? Well, this path will have a total cost of 10, Y's distance, which is 7, plus this edge with distance 3. So in total, this path has a total cost of 10 to get to X. What's X's current distance? It's 11, which is greater than 10. So we found a new shortest or least cost path. So in this case, we're going to update X's distance to 10, and then also change its predecessor in order to indicate that the least cost path would be the path starting at S, going to Y, and then ending at X. Perfect. Now we need to choose the next closest node. Well, it looks like there's a tie between X and Z, so we can kind of choose arbitrarily. Maybe your priority queue, if there's a tie between distances, might choose like by alphabetically or by node name. But literally it doesn't matter in terms of Dijkstra's as long as it always chooses the closest vertex or one of the closest vertices. Great. So now we move on to X and mark it as process. There's a single node, or there's a single edge going from X, and that's the edge from X to T with cost 2. Well, what is this cost of the path going from, of the path that would be a result of going from X to T? That would be the cost of X, which is 10, plus the weight of this edge from X to T, which is 12. So this path would have a total cost of 12 in this case. Well, T's current distance is 6, which is half as large as 12. So because there's already, we found a path with shorter distance than this new path, we won't choose to update T's distance nor predecessor. And nothing happens. Finally, there's one node left to process. We mark it as process, and there's one edge going from Z to another node, in this case, X. Z's distance is 10, and this edge has weight 7. So we found a new path with total cost 17 going from S to X. Is 17 less than X's current distance? No, because X has a current distance of 10. So nothing will happen. We won't update a distance nor the predecessor. And yeah, we finished running through Dijkstra's. And now we have this list of predecessors, which we can follow back to form our shortest, or I guess like least cost tree. That's like how I would like to refer it to. SPT is shortest path tree as well. Those are the same, but it's nice to make the distinction between the path with the least number of edges and then the paths with the least cost in case of a weighted graph. Awesome. And then why it works. So it works because of our rule of always visiting vertices in order of total distance from source. We always add the closest unexplored vertex to be processed next. And by maintaining this invariant, we'll always update distances in a way and choose vertices in a way such that we'll form our least cost tree, which I think is really cool. We're applying a single rule to eventually generate this least cost tree. And it works like magic. That's all the content I have for you in this section. We'll be diving more into graphs in this upcoming week, so stay tuned for that. Have a good one, y'all.